Hi, in this video, we'll be discussing on how we designed and created our laser tracker project. This project is being presented by Nick, Dejan, Yash, David, and Zach.
As you can see in the circuit diagram, we grounded the enable pin in the buffer gate as well as the source in the MOSFET. After this, we made sure to connect the positive end of the laser to 5 volts and the negative end to the drain, so that way the laser could turn on and off without any issue. One inherently tricky connection was in ensuring the data pin was placed in the correct input, since we sometimes had issues with accidentally pulling out all the wires and we had to recreate the circuit multiple times during testing. Most of these issues could have been solved by us soldering the circuit components in a printed circuit board or a custom PCB. The only reason we didn't develop one was mostly due to both time and financial constraints, since we only had a couple weeks to test the project, and PCBs can get expensive if you want everything as compressed as possible. For the circuitry of the laser target tracker, we needed to create a pull-down resistor circuit for the laser. This was created so that way any excess current generated by this project can be safely disposed of in a common ground. We initially had issues with the laser flickering, which we attributed this to being caused by a PWM signal being emitted by the data pin in the pan tilt hat. Later we learned that not only was a PWM signal being emitted, but the data pin was only releasing 3.3 volts instead of the 5 volts necessary for the laser to be powered on. In the end, we overcame both of these problems by hardwiring the data pin 40 on the Raspberry Pi to the circuit. After that, we amplified the voltage using a bus buffer gate to increase the data voltage from 3.3 volts to 5 volts, so that way the laser can successfully be turned on and off from a normal Raspberry Pi data pin.
For our library, CV2 is importing the OpenCV library for image processing. PanTilt is for our pen tilt device, which would just move the servos up, down, left, right. NumPy is for when we use Matrix to do larger operations in terms of uh, taking an image processing and converting the individual pixels from blue to what we need, which will be later discussed. Then time for line for sleep, for the code to wait on us for a number of time. RPI.GPIO is to access specific GPIO pins of the servo, or I meant the laser to turn it on and off. Next, we set the frame width and height, 640, 480, and then we initialize the camera to be upside down because the camera, oh, we have it upside down, so we just flip the frame, and then this is where we actually set the width and height of the frame. Right here, we have the settings for laser control, so we uh, set it to pin 21, and then we set it up as a GPIO output. Now we have function for clamping. Clamping is just used to set the range of the pan and tilt servos to be between 0 and 180 and not to go outside those ranges. And then now is a function to calculate the center zone. For calculating the center, we find the center of the object that we're going to give it, which is going to be an input, and then we're going to find halfway of the object from the center to halfway point, and that's going to be zone that the laser should be within. Now we set the initial values of the pan and tilt angles, which is -45, -45, which is a good angle, which is the angle that is best for being in the center that we've tested. Then we set that for the pan and tilt, and then we set the sweep direction to 1, so it sweeps counterclockwise initially when the searching. Now these are setting the blue values, the low and highs of the blue values. So we use NumPy for the range of arrays, the array range that we're using. And then this is the main while loop that keeps on continuously running. First, we set the GPIO pin to low, so the laser is off, and then we read the frame from the camera. And once again, this is where we flip it again, flip it vertically, and then it's just an error handling message. If the frame's not found, that gives the error. Next, we go on to convert the BGR values to HSV and create a mask for that to find the blue object. And then we go to find an object that is blue. And then if we do find a blue object, then we have to find the largest blue object if there's multiple blue objects in there, and then we get the center of that blue object. Then this is just to draw the green circle around it after that object is identified, and then draw the red dot at the center. And then once we find a radius that is greater than 10, which is a large enough object about the size of the frisbee that we have, we set the laser to high, the pin to high, and then we find the set how the distance between the center of the frame and this where the object is at. We go ahead and move the servos to where they need to be at, which is where pan and tilt. So we find the distance between the center and we clamp that so we're not going to out of range. And if this whole while if nothing is found, if no blue objects are found, then it's going to sweep left and right, which are this is the code to sweep left and right. And we wait for a second so it doesn't, we can vary the time how fast it spans in and out. Now, this is just to show the frame that what we're looking at on the screen. And if we press Q, then it exits. And afterwards, we clean up everything.
As with everyone else, I assisted Yash, Team 16's programming overseer, with our program. We were experiencing an issue with the camera moving up and down instead of locking in place when the frisbee was further away. We refer to this issue as jittering. We spent a lot of time troubleshooting this issue, as the problem initially seemed intertwined with overall system latency. Our solution was to establish a dead zone, or threshold, which prevented the camera from moving drastically when the frisbee slightly changed position. This relatively small change kept the laser on the frisbee with a much greater consistency. My assistance with coding optimizations in tandem with many iterations of 3D prints helped Team 16 create a robust, consistent, and entertaining final project. For the future, we collectively envisioned a second camera that would allow for depth tracking via triangulation. My favorite thing that I experienced working with Team 16 was our communication skills. We were able to keep each other accountable through collaboration and highlight each individual's skills to create an efficient and motivating work environment. By working as a team, we were able to come up with ideas such as hunt mode, frisbee laser activation, and variable speed adjustment, known more colloquially as tuning.
In this video, you
My
can see
name
the
is
final
Zachary
part of
Hurst,
our
and I'm going
project,
to be going
its
through an
completion.
explanation of
Some challenges and
problems
bottlenecks that
ran
we
into
encountered
operating the laser guidance
were
system.
summarized in
So,
three
the first issue
categories.
we had
Our
was some
software
software
challenges. These
challenges.
issues were in adjusting
Basically,
in the
the
delay
point
of
of
taking
our
in our input
laser
image
guidance
and
system
optimizing it so
was
our
to
system was
track and
responding the
follow a
fastest
blue circling
without the
target,
camera having to readjust
and
and move up
while
and down
tracking, it
randomly.
should point a
Our next
LED
category
laser light
is
at the
circuitry
center of said
challenges.
target.
These
What would
issues
happen is
stem
that the
from the fact
code,
that
it
we couldn't
loops
connect
every
the
10
input from the pan
milliseconds, so
tilt
it has a
hat to
delay
pull down
of 10
resistor
milliseconds.
circuit for the laser. This issue was
It
resolved
would
by
get to the
forcing a
center
wire
of the
into the hole
centroid of the
connecting the
object,
Raspberry Pi to the
and
pan
then it
tilt
would say,
hat
hey,
and
the
implementing
servos can only
a
move
voltage amplifier
1 degree at a
IC
time,
that
so it
was
moves up,
used to
down, left,
increase the
right, and it's
voltage
still not
generated
in the
by the Raspberry
center.
Pi
It
input
would then,
and
at the
making it
next
large enough
iteration
so
of the
that the
loop,
laser can
try
remain
to move
bright
towards
in the
the
pull down
center
resistor
again,
circuit.
and that would cause it
Our
to
final
jitter
category was
and
the
move
3D
around and
printer
not stay
challenges.
stationary once it
These
actually hit
issues
its
can be
closely
characterized
approachable
by
target.
adjusting the 3D
To
printed
fix this, we
box
added
and
a
laser holder
tolerance
multiple
range
times
where if it is
due
within a
to the
certain
printers
area
not correctly
of the
implementing
target
our
center,
measurements.
it actually
As
will
a
not
result,
move.
we had to
We can also
create
fix this by
many
getting better
prototypes in
software
developing our system,
with
which cost us
more
a lot of
teeth that
time to
is
develop.
less than a degree at a time. The next issue we had were issues with some circuitry with some hardware. So we had created a transistor circuit with a pull down resistor in order to turn off the laser. Now, as this circuit was used to turn on and off the laser, we needed to use the Raspberry Pi 4 to connect to it. But all of the outputs for the Pi 4 were connected to the pan hat tilt, and there was no way with the way that we had it set up to connect the pan hat tilt to the actual transistor layout. All we could do is connect a data pin that would send a PWM signal. What we ended up having to do was use a power pin at 3.3 volts, convert that to 5 volts, and then use that and connect that to the transistor itself in order to turn on and off the laser. Another challenge we had was using the 3D printers in the makerspace. While we as a group are very grateful for having that as a resource and being able to 3D print parts, it was incredibly helpful in this project. Unfortunately, the printers that are in the makerspace have a larger tolerance than we would like when designing and creating objects. So we would create an object that was measured and created correctly and have to do 3 to 4 prints of said object in order to get one of the right size because it could vary to such a degree, as well as having multiple prints fail and having to get them reprinted. What we would do in order to solve this issue is have multiple of us go up at the same time and print 2 to 3 copies of a part that we may need, as well as if we have multiple STL files that need to be printed in the same day to create something such as a box or our holder or container for the project, we had to all go and print one of these files a day, as well as waiting with longer wait times. So some of these parts could take anywhere from, 2 hours on the short end to 23, 27 hours on the long end, depending on how large these files were. So that just took a lot of development time as well as a lot of hassle on our part to get the parts actually made correctly. We also had a multitude of other challenges. Feel free to ask us more detail about any of these other challenges or the ones that I've talked about here if you have any questions. Thank you.
And that concludes the end of our presentation. Thank you so much for watching.